Hi, my name is Konstantina Melu, and today I'm going to discuss a key problem that cloud providers face on a daily basis: how to allocate virtual machines on physical servers efficiently. Cloud computing has grown immensely in the last decade. One of the main reasons for its success is the flexibility that it offers to the users. Users, which includes companies, do not need to incur large expenses to purchase their own computing power. Instead, they can easily request compute resources based on their needs at the time. Cloud providers operate large data centers, and users can run virtual machines, or VMs for short, on demand. Cloud providers have many physical machines in the data centers. When VM requests from users arrive, they place the VMs on physical servers that have enough capacity to serve them. Efficient allocations decisions are crucial in this setting. Inefficiencies lead to fragmentation and the need for more machines or higher power usage. Our goal in this work is to design algorithms for allocating VMs to physical machines so that the total time the machines are used is minimized. This problem has some similarities with the dynamic bin packing problem. We can think of the VMs as items that arrive and depart over time, and we need to pack them into bins, which are our machines. However, we do not minimize the number of bins used, rather the total duration for which we use them. From now on, we will refer to the VMs also as intervals. Each interval I has a length Li, which is its duration, and a width or size Wi, and you can think of this as the CPU that it requires. All sizes are between 0 and 1. We will discuss two settings in terms of the widths. In the first, all VMs, or intervals, have the exact same width, while in the second, the widths are arbitrary between 0 and 1. Regarding the physical machines, we will refer to them simply as machines. We assume that the width or size of its machine is 1, and we say that the machine is active or open when it has at least one VM running on it. Our goal can then be expressed as follows. How can we pack the intervals to the available machines so as to minimize the total time that the machines remain active? We assume that we have enough machines to schedule all the VMs, so no rejections are necessary in this setting. One important notion for this problem is that of the load vector V. This is the histogram of the VM capacity that is required over time. So at each time t, the value of Vt is given by the sum of the sizes of the intervals that are active. This also gives us a minimum number of machines that is required at that time. For example, if at time t we have 3 active VMs, and each of them has a size of 0.5, we know that we need capacity at least 1.5, which means at least 2 machines. So if we sum this Vt over the whole time horizon, this also gives us a straightforward lower bound for the problem. In the online setting that is the focus of this talk, the VM requests arrive over time. The precise arrival time of each VM is not known ahead of time. When a VM arrives, its width or size is revealed to the scheduler. In the clairvoyant case, the VM's lifetime also becomes available upon its arrival. The best result in this setting is by Azar and Weinstein. They show a no square root log mu competitive ratio and show that it is optimal. The competitive ratio is a way to evaluate how well an online algorithm does. So it compares the solution of the online algorithm with the optimal solution for the offline case. For example, if we have a competitive ratio of 2, that means that the online algorithm pays at most double the cost for the offline one. Here, mu is the ratio between the longest and the shortest interval length. You can take large values in practice because the VMs can be very different. So we might have very short ones that last a few minutes, or very long ones that run for weeks or months. Now this result uses the values of the VM lifetimes. However, in the past few years, cloud providers have developed machine learning systems that can provide them with increasingly richer statistics. So motivated by these advances in machine learning that provide good estimates of workload characteristics, we ask, can we leverage this additional information to improve the algorithm guarantees? We look at two sources of additional information besides the VM lifetimes: the future load vector and the average load. The future load vector is the histogram of the upcoming demand. Since that is an aggregate over all VM requests at any time, it can be predicted with much higher accuracy. We show a constant competitive ratio, which is 2 for the uniform case, which will be the main focus of this talk. The average load is just a single number, so this is the total load divided by the length of the time horizon. It turns out that just this value, which can be estimated with very high accuracy, can improve significantly the performance of the scheduler. So a different way to express this result is as paying the optimal cost opt plus an average additive term of square root the average log nu at each time t of the horizon for the uniform case. Now, for the remaining of this talk, I will go into more details about these algorithms. And let us start with the online covering algorithm that uses the future load. So what do we mean by covering? So consider this example. So here we can see for each of these intervals the time that they arrive, their start time and their end time. And all of them have the same size. So we assume here all sizes are 0.5. So we are in the uniform case. A cover is a set of intervals that cover the time horizon with load between a minimum and a maximum value. For example, these two blue intervals cover the horizon, since for every t between 0 to 19, so for the whole horizon, there is at least one active interval in the cover. For the min and the maximum value, consider a 1 to cover. These four blue intervals form a 1 to cover, since the load everywhere is between 1 and 2. So remember here we have each of them has a width of 0.5. And the only exception is when the total load is actually smaller, so this is still fine. Now, why are covers useful? A cover can be easily scheduled on machines. In the uniform case, we just saw that a 1 to cover at any point has load at most 2. So 2 machines that are open for the whole time horizon are sufficient to schedule all the intervals in the cover. At the same time, each cover has load everywhere at least 1. So for each time, we are using at most 2 machines to schedule at least 1 unit of load. As a result, if we consider the offline problem, we managed to show a 2 approximation algorithm, and the way we do that is by first showing that we can construct covers efficiently, and then iteratively creating covers and then schedule them together, and then removing them from the instance until we schedule all the intervals. The problem here is that to construct these covers, we need to actually have information of the full instance. So we need to know exactly when its interval arrives, how long it stays, when it departs, etc. And in the online case, we don't have that information. So what can we do? Here we developed the online covering algorithm. And this algorithm creates a set of covers in an online fashion. So the algorithm consists of 2 components. A method to create single covers, where upon its interval arrival, it decides whether to accept the interval and make it part of the cover or reject it. Then we have an algorithm to create multiple covers, and this is our main algorithm. It runs multiple copies of the single cover algorithm, which generate a set of covers. And then each of these covers can then easily be scheduled on machines. So at the beginning of the execution, you can think of having a set of empty covers for intuition. Each cover runs its own copy of the single cover algorithm separately. The algorithm takes a load vector estimate V prime as input for the future load it expects to see. Then, when an interval I arrives, it needs to decide whether to accept it to the cover or to reject it. Each cover accepts an interval only if it needs it to achieve a target lower bound. In the uniform case that we're talking about here, you can think of each cover trying to get at least load 1 at its time. The cover will reject an interval unless it realizes that the rejection will not leave enough future load for it to reach the lower bound, in which case it will accept. What changes between the different covers is the future load they expect and the intervals they see in which they can accept or reject. These parameters are controlled by the main algorithm. Let's see how that works in action using the same instance as before. So the future load for the instance is available to the main algorithm. The first interval arrives at time t equals 0. The main algorithm first gives an opportunity to cover 1 to decide if it wants to keep it. Cover 1 also sees the whole future load. It looks at how much load it should still expect and whether this interval is necessary. It turns out that the remaining load, if it rejects it, is less than 1 for some time in the interval, so say between here t equal 1 and 2. So it accepts it and makes it part of the cover. A similar process is followed for the second interval, and cover 1 accepts that interval as well. Things are different when the third interval arrives at time t equals 2. The first cover looks at it first. Between times 2 and 10, the lower bound of 1 has already been reached, so there is no incentive to receive more intervals. Between times 10 and 14, the algorithm sees that it expects to receive a lot more load, so no need to keep this interval for now. Cover 1 rejects the interval. At this point, the main algorithm gives cover 2 the opportunity to get it. What changes here, though, is that the full future load is not revealed to cover 2. The main algorithm knows that cover 1 wants to keep load at least 1 everywhere, so it shows the future load as reduced by 1. The interval is needed by cover 2, so it gets accepted. Similarly, cover 2 accepts the fourth interval as well. The fifth is not needed either by cover 1 or cover 2, so it is accepted by cover 3. Cover 3 sees the future load decreased by 2, since the first two covers will have retained at least 2 units of load at each time. Continuing the same way, we assign all the intervals to covers, and this is the end result. This algorithm achieves a competitive ratio of 2 for the uniform case. Let me now give you some intuition on why this is the case. As we said, each copy is trying to create a 1-2 cover. If each copy knew the exact load it would receive, then it would successfully manage to do so. However, that is not the case. We said that cover 2 sees the future load as decreased by 1 because cover 1 wants to keep load at least 1 everywhere. But it might also end up keeping load more than 1 at some time t. So cover 2 will expect to see some load at that time that will never arrive because cover 1 has kept it. So this v prime is actually an overestimation of the load that the cover will receive. This overestimate parameter shows up in the guarantees for the lower bound. So we might not be able to form exactly 1-2 covers for the uniform case, but it turns out this is enough for our guarantees. In particular, we show a lower bound on the load that the covers will accept, and more specifically we show that the first j covers will accept at least a certain amount of load. We then use that to obtain an upper bound on the number of copies required to accept all load. This, combined with the fact that we can easily schedule covers using 2 machines, gives us the competitive ratio of 2 for the uniform case. This concludes the overview of the first algorithm. Let's now see how even the knowledge of the average load, which is just a single number, can help the algorithm obtain better results. This algorithm, instead of creating horizontal layers that cover the time horizon, it groups the intervals based on their length into classes. When an interval arrives, if the current load of the class is high, it schedules it on dedicated machines with intervals from the same class only. If the current class load is low, then it's scheduled on general-purpose machines with intervals from any class. The intuition here is that more compact scheduling can be achieved when the intervals are similar in length and arrive close together in time. Now let's look into these aspects in more details. The first question is how the classes are formed. Class J is determined using a parameter epsilon j. Although the exact definition looks involved, this is an example of what the classes look like. Intervals with length very close to 1 belong to class 1, and longer intervals to higher index classes. As you can see, the higher the class index, the larger the amount of length that it captures. The second question is about the low versus high load of the class. This is given by a threshold parameter qj that depends on the average load and the class index j. It is important to note that both the class limits and the threshold use the average load information. This information allows us to create good classes and split the load well in order to achieve our guarantees. Now what is left to see is how the intervals are actually scheduled. In the low regime, we schedule the intervals of any class in general machines, simply using first fit. In the case of high class load, we schedule these intervals separately with intervals of the same class. To do this efficiently, we develop a new family of non-clairvoyant algorithms. And in particular, we show a reduction that takes algorithms for the static bin packing problem, so this is the case where the intervals arrive but do not depart, and transforms them into algorithms for the dynamic case, which is our problem. Now, by selecting appropriately the algorithm to use as the base for the reduction, gives us the desired results. And in particular, if we use next fit, we obtain the results for the uniform case. And I will talk about the non-uniform in a couple of slides. So to conclude, we have seen two algorithms, each utilizing different kinds of additional information, the future load vector or the average load. We see that even with basic information, the single value of the average load, we can improve the performance of the scheduler. We have focused so far on the uniform case, where all VMs have the same size. However, we have also generalized these algorithms for the non-uniform case as well. Here we can see the results for the non-uniform case, and in the hybrid algorithm, we use the harmonic algorithm as the base of the reduction. So this k that appears here is the parameter of the harmonic algorithm, and pi k is a number that quickly approaches 1.692. An interesting question that arises at this point is how the prediction errors influence the results of the algorithms. We have already started looking into this, and in the paper we have results regarding the second algorithm, and show that it is robust to errors in the average load predictions, as well as show how the lifetime errors influence the results. So far, we have focused mostly on the fundamentals of the problem, but given that we have predictions for the VM lifetimes and the loads, our next step is to try them out in practical settings and see how well they perform in action. Thank you, and looking forward to answering any questions.